Okay, welcome back, students. We're discussing the actual diode characteristics. Actually, we had some issues in the last video, so let me discuss it again. If a device is obeying Ohm's law, this is Ohm's law that if you are increasing the amount of voltage will be here as the independent quantity, and current is a dependent quantity, which is also dependent upon the voltage, and you are keeping the resistance constant. So if this is a linear relationship, the device will be called a linear device. But in diode, the relation is not linear, and if you are increasing the amount of voltage, you can see that here this is voltage and this is the current. This is voltage current graph. You can see this is a transfer characteristic curve. This is what is this? This is transfer characteristic curve. So when you are increasing the amount of voltage up to certain point, there will be no current or very negligible amount of current. After some threshold value, you can see here that the threshold value is here is 0.3. After this voltage, the current will be increased in exponential manner, but non-linear, but not in linear manner. Similarly, here you can see that the current is also not increasing in a linear manner. These are basically two different devices. Here the threshold value is 0.3. Here the threshold value is 0.5. Sorry. The threshold value here is 0.3, while for this curve the threshold value is 0.5. So after 0.3, the current will be increased in exponential manner, but non-linear. That's why the diode is called a non-linear device. Okay, and this is a first quadrant. That's why this is called forward bias region. Forward bias again, we have discussed earlier. Sorry for my writing again. Forward bias region. Similarly, in reverse bias region, you can see that by applying the reverse polarity, initially the current will have some value. The current will be increasing, but after a certain point, the current will remain same and will remain constant at some point. This is due to the constant value of the leakage current or the reverse current. That's why this place is called, this quadrant is called the reverse bias region. Okay, you can see it here because here the voltage is negative and the current is also negative because this is in the opposite direction. Okay, so this is the actual diode characteristic curve which is explained here. Let's move on. We have discussed majority and minority carriers in each slide, and you can also see it here that majority carrier in types of are electron, while the majority carrier p-type materials are holes. Okay, and so on. Zener region. This is again a very important topic. You can see here that this is again the diode characteristic graph. This is the forward direction. This is in the forward direction, while this is a reverse direction. I have explained it earlier that in the reverse direction, when you will be increasing the amount of voltage, the amount of current will remain same. Here you can see there the amount of current is same, but there will be a point, this VZ. There is a point where by increasing the amount of just a minute. So thereby the current will be having a constant value, but after some time the current value will drastically increase and it will become almost infinity at certain voltage that is called V of C. This voltage or this region where the current suddenly increases to the infinity, suddenly increases to the infinity, this region is called Zener region because now Zener diode cannot bear the reverse voltage, and it will open the ways, and all the current, all the charges it will have will find its way towards towards the reverse direction. Okay, so that is the Zener region. You can see it here, there is the diode's reverse bias region. At some point, the reverse bias voltage is so large that the diode breaks down. Okay, this is again also called, this reverse direction is also for the breakdown region, because now the diode is breaking down and allowing all the charges to move in reverse direction. This is the breakdown region. Before this V of C, that is called the Zener region, there will be a value after which when you will increase the after which when you will increase the voltage value, it will enter the Zener region of breakdown region. Okay, this is the breakdown region, and that when you will increase the amount of voltage, very small increase in the amount of applied voltage will cause the breakdown. That value is called peak inverse value. Let me give you an example. Let's say you are increasing the voltage from 0 to, you have increased the value from 0 to 10, and the amount of current has remained constant to 1 milliampere. Okay, as you increase the amount of value to 10.1, the current suddenly becomes 10 milliampere. Okay, so this is, what is this? This voltage is called V of C or Zener voltage, and this voltage, this 10 volt, is called peak inverse voltage, PI. This is the maximum amount of voltage. This is the maximum amount of reverse voltage which any diode can uh, bear in reverse direction. Okay, so that is the concept of Zener region. Okay, so let's move on. Forward bias voltage. Forward bias voltage for different diodes are given in this slide. The forward bias voltage for gallium arsenide diode is 1.2 volt. Silicon diode is, for silicon diode is 0.71. For germanium diode, this is 0.3 volts. Okay. The amount of uh, forward bias voltage is this one. And this voltage is also called a knee voltage, because I have told you earlier that up to certain point when you are applying the voltage, so up to certain point the value, the current in the diode will be zero, but when that value surpass, it will be increased in, as a no as in an exponential manner. Okay, in the exponential manner. So what are these voltages? Let's say this is V of K. So for any diode, in any diode, the voltage, if you are applying to the diode, should surpass these values for conduction purposes. So for the germanium, V of K will be zero point 0.3 volts. For silicon, it will be 0.7 volts, while for gallium arsenide, it will be 1.2 volts because below these values, below these voltages, the diode will act uh, as an open switch. Okay, so this is this region, and when you will surpass this value, the diode will be conducting will behave as a conducting wire. Okay. Temperature effects. As this is a semiconductor device, so by having higher temperature, the forward bias voltages will be reduced. The amount of the forward bias voltages will be reduced. Let's say you have 40 degrees centigrade and you are applying zero point 0.3 volts to a germanium, so its conduction will be it will be conducting after zero point 0.3 volts. But when the temperature is increased up to 60 degrees centigrade, its biasing voltage, or you can see that the knee voltage will be reduced to the 0.29 or 0.28 volts and so on. Similarly, the increase the amount of temperature, the increase in temperature will increase the amount of reverse current. Okay, the amount of reverse current will also be increased by increasing the amount of increasing the temperature of a diode. At it increasing maximum reverse bias avalanche voltage. When you are increasing the temperature, it will increase the reverse voltage as well. Similarly, it is written here that germanium diodes are more sensitive to temperatures. Germanium diodes are more sensitive to temperature. So, if temperature there are some variation in the temperature, so germanium diodes will be more sensitive and their characteristics will be changed. While silicon gallium arsenide diodes are more stable and has robust performances at different temperatures. That's why gallium arsenide are most commonly used due to their performances at higher temperatures of gallium arsenide diodes due to their performances or robust characteristics. Resistance levels. We have earlier discussed the characteristics of diode, and we saw that the diodes will be behaving as a short circuit for the forward bias region, and will act as an open switch for a reverse bias conditions. But that were all the cases for ideal diodes. So when we are considering the actual characteristics or actual scenario, there will be some type of resistance related with the diode because it has certain material, it has connection wires and so on. So every connection wire, every conductor has some resistance, every material has some resistance, every semiconductor device has some resistance. So therefore we should consider it for analysis reasons. So the diode has three types of resistances: DC or static resistance, AC or dynamic resistance, and average resistance. Okay, let us calculate these. So the first one is the DC or static resistance. The DC or static resistance can be calculated at certain point at the take any certain point, and at that point calculate the amount of voltage, calculate the amount of current, and then apply this formula, and you will find the static resistance at that point. Okay, this is very easy. Again, you know the formula: V is equal to IR. This is Ohm's law, which we have discussed in our in week 5. So if any two of these formula is known, you can easily find the third one. Okay, so here you know the value of voltage, you know the value of current. You can easily find the value of resistance, which is the static resistance, and the uh, amount of the resistance will be changed when you move the point from one place to another, and this is due to the nonlinear characteristics of this curve. Okay, uh, so this is the static resistance forward direction. Similarly, this is the AC or dynamic resistance. Just keep in mind that the AC resistance is this one, which is dependable upon this V and this I of t. Okay, this is the AC or dynamic resistance, but we will consider it while we will be using small signal amplification in BJT circuits. So just keep in mind this formula, and that's why we are going forward. This is the AC resistance. This is the average AC resistance. This thing is very important. In order, in spite of finding the resistance at one point only, here it is considering 2 points. It is considering this point and another point, this one. Okay, so it is taking this difference, this this value minus this value. Let's say this is I2 and this is I1. Similarly, the value here at I1 is V1 and here this is V2 for I2. So just find the differences between them. So V2 minus V1 is equal to delta VD. Similarly, I2 minus I1 is equal to delta ID. Okay, so now I divide this one by this one. So this is the rate of change. This is the rate of change of the resistance. That's why this is the AC resistance by applying this formula. This is from point to point, and this gives us the average resistance, average AC resistance. This thing is very easy to calculate from any graph. Let's move on. This is a diode equivalent circuit for representing any diode circuit. I have told you that in any diode, let's say this is a silicon diode. So for silicon diode, the voltage drop is 0.7. So it is represented by a voltage source, a resistor, and an ideal diode. For forward biasing, if we are applying here the forward bias, let's say in this model, if we are applying forward bias, so this is the ideal diode. It will behave like short circuit. The resistance will be found by the calculation which we have done previously, and this is the voltage for which it has to surpass for conduction. Okay, for a silicon, this value is 0.7. Okay, this value is 0.7. If this was a germanium diode's value here would be, if this was a germanium diode, so value here would be 0.3 volts. Okay, so this is the diode equivalent model, because every diode has a resistance, every diode has some voltage drop related with that diode, and by applying the ideal voltage, ideal diode here, we can map any diode in its equivalent circuit. Let's move on. This is the diode capacitance. Just leave it at this point. Reverse recovery time. What is the reverse recovery time for any diode? If any diode is conducting in a forward direction, okay, if any diode is moving in a forward direction, let's say you can say that if this is a diode and it is moving in this direction, and certainly, uh, you suddenly change the voltage, applied voltage to from forward bias to the reverse bias, it will move here and it will be moving like this one. So this change, so where at this point it is moving in the forward direction, and after some time it will be moving in the reverse direction. This is called reverse recovery time. It will be moving in the reverse direction in this reverse recovery time. So reverse recovery time is the time required for a diode to stop conducting once it is switched from forward bias to the reverse bias. Okay, so this is that point where it will be where it will stop conducting and will be changing its direction. Just like if a car is moving and you want to change the direction, like you want to reverse the car. So if it is moving in the forward direction, you want to reverse it. Since for some time you will have to apply the brake and it will stop. So that time the time for which it will be stopped is called the reverse recovery time. Okay, I think now it's understandable. Diode specifications. So what are the diode specifications? The diode specification can be forward voltage in any diode. These are all the specifications which are related to any diode. These are the forward voltage, maximum forward current, and if you are applying more than this current, the diode will be burned off. Reverse saturation current, okay, reverse voltage rating PIV or PRV, we have discussed it. Maximum power dissipation, it is related to these currents, capacitance recovery time, and operating temperature range. If the temperature range is not given, the temperature range of any diode should be given to operate in a certain um, feasible temperature ranges. Otherwise, it will not run. Okay, these are the symbols of a diode. These are different symbols and packaging. Uh, this is the first symbol. This is used in circuits, and these are different diode packages which are commercially available. The node is abbreviated as A, the cathode is abbreviated as K, as we have discussed earlier on. Similarly, if in any packaging you have a diode, in any circuit you have a diode, the diode symbol is generally like this one, and it has a band over it. Okay, it will be like this cylindrical shape. It will be cylindrical shape like this, and it will have a band here, just like here. So the band area, the band is the indication of a cathode. This is for a cathode like this. It would be okay. So this diode is this one. Band will be representing this area. So this is the diode. These are the diode symbols used in real life. Diode testing the characteristics of a diode, that the diode is functioning or not. So there are three devices: diode checker, ohm meter, and curve tracer. More frequently, ohm meter is used for checking the resistance of a diode. That if a diode is conducting, if a diode when a diode is conducting, is forward region or is forward direction, resistance will be very lower, while the reverse region resistance will be very higher due to the unidirection characteristics of a diode. So let's see the diode testing mechanism. Diode checker is many digital multimeter have a diode checker functions. Okay, so the diode should be tested out of a circuit, and for those the following forward bias voltages will be found when the diode checker is applied. It is nowadays available with many multimeter devices. Uh, Similarly, when you are using meter, you have a diode, you know that where the anode is and where the cathode is. You will just apply different leads of an ohm meter or a multimeter while its knobs are set upon the ohm meter. So red wire will be applied here, and black wire will be applied here. And let's say I have mm, let's say I have an ohm meter here. It has terminals. It has a screen. Okay, so this red is the indication of the positive terminal or positive supply, while the black is the negative or common supply. So when these are when the voltage, these are just like the applications of the voltage. So now here the uh, diode is forward bias, and it will be having like short circuit, or will be having a very small amount of resistance. So here, if the resistance is very small, and here when we will reverse the direction, um, just like applying positive here and negative here with the same for the for the same diode. And now, if now the um, resistance will be very high, so it means the diode is fine and working very perfectly. If now in the reverse direction the resistance is high as mentioned here, and for the forward biasing the resistance is very low. Okay, so the diode can be tested here. There is another mechanism which is called the curve tracer, and in that curve tracer we can draw the curve of a diode, and by applying different voltage values, this is the curve tracer are the variable. Just like in electrical department, we have a oscilloscope, and on over that oscilloscope you can apply different values of voltages, and after applying the voltage you will find the current flowing through that device, and that curve tracer or that oscilloscope will draw a circuit, a graph like this one, and you can see different characteristics of a diode through this graph. Okay, just like the voltage is here, and after surpassing this voltage, it will be conducting in an exponential manner. Okay, so these are basically three mechanisms for testing a diode. Other types of diode, there are many other types of diode, and the most famous ones are the Zener diode, light emitting diode, and diode arrays. We will not be considering diode arrays now, but let us discuss Zener diode and light emitting diodes, LEDs. So this is the symbol of a Zener diode. A Zener diode is a diode which works in the reverse direction. Okay, we have earlier that there are different regions of a diode, just like this one. This is the forward region, and this one is the reverse region. Okay, so we have saw Zener voltages, and this is a diode. This Zener diode works in this region, and the application of this Zener diode are the voltage regulator, because here you can see that when the current is suddenly increase, the value of voltage will remain constant here. This is V of C. So this characteristic of this diode are used as a voltage regulator circuit. We will consider it and we will study it in later chapters. This is the symbol of a Zener diode, and you can see that the cathode of a Zener diode is connected positive supply, while the anode is connected with negative supply. So it works in a reverse bias. It works in reverse bias regions. Okay, this is the reverse bias region, and reverse biasing is applied over region and diode. LEDs are nowadays very famous, and the basic function of a light emitting diode or an LED is when we apply the voltage over an LED, the uh, the conduction of charge is always is always producing the amount of uh, light in the region which is visible, or in the region which is not visible, just like infrared. And that is the basic principle of light emitting diode. The symbol of a light emitting diode is this one. Okay, um, so that's it. These are basically the diode arrays, and we will discuss these arrays in later chapters. So that's it. This is all about the introduction of semiconductor diodes. We have discussed the basic functionalities of a diode, what are the different types of diode, what is a characteristic curve of a diode, the functionalities of a diode, its application, and so on. So in next class we will discuss different circuits of diode where it is applied. So I think it's enough for today. Please listen every instant of this lecture very carefully. Study it through your book, and ask me any question in your interactive session, which will which will be scheduled at the same time where when your class will be. Okay. So I think it's enough for today. Thank you so much, and I will see you in the interactive session. Thank you so much. Allah Hafiz.